Assalamu alaikum everyone. Today we are going to cover lecture number 22 and this is week 11. Today's topic is oscillators. This topic is covered from chapter 8 of book Op-Amp and Linear Integrated Circuits, 3rd edition by Ramakant Gaikwad. These are the lecture contents: definition of an oscillator, types of oscillators, square wave oscillator, relaxation oscillator. There are different types of oscillator, but in this class we are going to cover only square wave oscillator, which is also called a relaxation oscillator. Then we will see working of square wave oscillator and derivation of for computing the time period and frequency of the output square wave that is produced by the oscillator. So how the timing analysis is performed to find out the frequency of and time period of the output waveform that we will carry out for the square wave oscillator that we will cover in this lecture. So first of all, definition of the oscillator. What is an oscillator? An oscillator is a circuit which produces a continuous, repeated, alternating waveform without any input. So it is here represented by a block which constitutes a circuit which produces an output without any input to this oscillator. Only the requirement is that it requires a DC source from which this circuit would produce an oscillation. So what the oscillator do is, oscillators basically convert unidirectional current flow from a DC source into an alternating waveform of the desired frequency decided by its circuit components. So what oscillator do? Oscillators basically convert a unidirectional current flow from a DC source into an alternating waveform that would be produced by the circuit of the desired frequency, shape, and time period, and the output would be decided by its circuit components. So whatever the oscillator is made up, what type of components and what are the values of those components, depending upon those components, the output would be defined by the oscillator. The output would be defined so values of these components would determine the output produced and the frequency of the frequency and shape of the output signal. So next is types of oscillators. So there are different types of oscillators. For example, square wave oscillator, triangular wave oscillator, sawtooth wave oscillator. Then we have sine wave oscillators and PWM signal generators. So the types of oscillators are based upon the shape of the output signal that they are producing. In some oscillators they produce square wave, triangular wave, or sawtooth waveform. Some other oscillators produce sine wave or cosine wave, and also the PWM pulse width of the output signal produced, they can be changed by oscillators of kind PWM generator. Next is what is required from an oscillator. So these are the requirements for an oscillator. Number one is the shape of the desired signal. So for an oscillator of any kind, what is the shape that is required to be produced by an oscillator? This is the first requirement. Then we required the particular time period of the signal that is required to be produced. For example, I want to produce a signal of 1 millisecond time period and of frequency 1 kilohertz. So the frequency, what is the frequency of the desired signal required from an oscillator to be produced? Then pulse width or duty cycle of the output signal in case the output is a square wave. So based upon these requirements, we look into the oscillator and see what are the parameters which control the shape of the signal, the time period of the output waveform, frequency of the output, and PWM or pulse width or duty cycle of the output signal. So let me start with the square wave oscillator or a relaxation oscillator. So this is the circuit of a square wave oscillator in which an op-amp is used along with some resistors and a capacitor. So for an oscillator, the capacitor is an essential requirement. Without a capacitor or an inductor, so without any energy storage element, we cannot implement an oscillator. So you may have come across the sinusoidal oscillators in which an inductor and a capacitor can be used to produce a sine wave, but the simple LC circuit cannot produce continuous sinusoidal output or sustained oscillations because as time goes, the the energy stored in the capacitors or inductor keep on dissipating, and as energy goes on decreasing, the oscillation starts dying out. So you have to refresh that energy after certain interval of time so that oscillations can be maintained. But in the circuit, this op-amp and the associated DC battery will make the energy refresh of this capacitor on a continual basis, so that you get a output that would be sustained for indefinite time. So how the circuit would work, that we will see in the coming slides. So first of all, look at the circuit and see that there are the op-amp is connected in feedback, and there are two types of feedback in the circuit. One is the positive feedback, you can see here, and the other one is the negative feedback. So both feedbacks are applied in the op-amp. So how the circuit would behave in the presence of both feedbacks, that we have to see. So whether this op-amp is treated as a negative feedback amplifier or a positive feedback amplifier, this is the question that we have to address. अगर ओपम में दोनों फीडबैक्स कनेक्टेड हों तो फिर आप ओपम को किस तरह से देखेंगे? क्या फिर भी जो वर्चुअल शार्ट का कंसेप्ट होगा वो कब इस केस में वैलिड होगा या नहीं होगा, चूँकि इसमें नेगेटिव फीडबैक लगी हुई है? और क्या आउटपुट सैचुरेशन में जाएगी या नहीं जाएगी? क्या ओपम का गेन इस केस में कितना होगा? क्या पॉजिटिव फीडबैक अगर कनेक्टेड है तो इसका गेन हाई होगा या फिर नेगेटिव फीडबैक की वजह से इसका गेन जो है वो रिड्यूस्ड है? तो अगर इसमें पॉजिटिव फीडबैक कनेक्टेड है तो आउटपुट क्या सैचुरेशन में जा रही है या नहीं जा रही? तो ये सारी चीज़ें देखने के लिए जो हम अप्रोच यूज़ करते हैं वही करते हैं कि इसमें देखते हैं कि कौन सी फीडबैक डोमिनेट करेगी, क्योंकि एक तरफ नेगेटिव फीडबैक भी कनेक्टेड है और पॉजिटिव फीडबैक भी कनेक्टेड है। तो फिर ये देखना पड़ेगा कि इन दोनों में कौन सी डोमिनेट करेगी। तो जो भी फीडबैक इसमें डोमिनेट करेगी उसकी वजह से जो ओपम है उसका जो ऑपरेशन है दैट वुड बी गवर्न्ड based on that feedback. So if negative feedback is dominant, then the virtual short concept would prevail, and if positive feedback is dominant, then the virtual short condition would not be satisfied and output of the op-amp would be in saturation and would be in one of the supply levels. So इस केस में अभी हम अज्यूम करते हैं कि जो पॉजिटिव फीडबैक है वो डोमिनेट कर रही है। उसकी वजह यह कि इसमें जो पॉजिटिव फीडबैक है दैट इज़ कमिंग फ्रॉम द रजिस्टर्स, एंड वी हैव सीन दैट with our experience that whenever the feedback is through resistors it always dominates. Otherwise we have to derive the transfer function of the circuit, and from that we can find out the location of poles, and from that we can see that whether the circuit is having a positive feedback dominant or a negative feedback is dominant. That is when if the poles of this pole of the transfer functions are on the right of plane, then the positive feedback would be dominant, and if the poles are sitting on the left of plane, then the negative feedback would be dominant. For the square wave oscillators, the positive feedback would always be dominant, and the output would always be in saturation. That is, either output would be at plus VCC or at minus VCC. That is either high or low. So you know that for a square wave, the output is always at one of its two output states. That is, either output would be at plus VCC or at minus VCC. So for example, this is at 0. This is 0 level, and output would be at plus VCC or minus VCC. That is, it jumps from one level to the other and keep on jumping in this fashion. So in order to see how this circuit works, we see that there are both feedbacks applied in the circuit, but the dominant effect will be due to the positive feedback, which results in a gain greater than the open loop gain. So output would always be saturated, that is, output would be either plus VCC or minus VCC. So these are the two supply levels which are connected in the case of oscillator, and there is no input applied, only these power supplies are connected, and you will get the output which would be oscillating periodically. To start with the analysis, we assume that the output is one of its supply level, that is either plus VCC or minus VCC. So towards that, let we assume that output is at plus VCC. So if output is at plus VCC, then what would be the voltage at node V1, that is here? That can be computed using this equation. V1 is equal to R3 into VCC divided by R2 plus R3. So this is the voltage that is developed at this node. As long as the voltage at this point is VCC, the voltage at this point would be defined by this relationship. Also, we assume that initially capacitor is discharged, and now with the V out is equal to VCC here, this capacitor would start charging through this resistor through this path. The current would start flowing in this path due to this voltage appearing at the output node. The current would start flowing in this connection and start charging the capacitor. So this current would flow into this path. In this connection, the current would be 0. So whatever the current is here, that would flow into this capacitor. So the capacitor would start charging through R1 towards VCC as shown in the next slide. So in this graph we are going to see, number one, the voltage across the capacitor, how this capacitor voltage is developed, that the capacitor would start charging up at with a time constant. So this is the voltage across capacitor V2, this green plot. So this waveform in green color represents the voltage across the capacitor, and the one in black color is representing the output of the circuit. This is the output. So the capacitor voltage would start charging from 0, as we are assuming that initially capacitor is discharged for the first time when the circuit is powered up, and the capacitor was initially uncharged, and it would start charging, and it would keep on, the voltage of the capacitor would be charging towards VCC. Now this capacitor voltage is applied to the inverting terminal of the op-amp, which is defined as V2. And the voltage at the non-inverting terminal, which is defined as V1 and is equal to this value, which is the trigger, which is also the trigger point, VUTP. That is this op-amp now start working as a comparator, and it would compare the voltage that appears at its terminals. Whenever the voltage of the negative terminal becomes higher than the positive terminal, the output would flip into the negative saturation level. So this voltage was equal to VUTP, and this voltage, the voltage of the capacitor was increasing, and when it reaches the level set by these components, then what happens is the output would shift to the negative saturation. So initially it was at plus VCC, then it would flip to the negative VCC. So this is a negative VCC actually, this is minus VCC. So when voltage becomes minus VCC here, then what would be the voltage at V1? So this voltage would become minus R3 into VCC divided by R2 plus R3. So let me call it as LTP, VLTP, which is at the lower trigger point, and it is some negative value. So this voltage would become negative. And what about the capacitor voltage? As the output becomes minus VCC, the direction of current would start reversing. That is, current always flows from higher potential to the lower potential. So the right hand side potential is lower than the left hand side potential, where initially the capacitor was charged to this value, positive value, and what happens is when output goes to negative, then this capacitor would start discharging, and it would start charging towards minus VCC. So at this point, at this instant where output was changed to minus VCC, then capacitor would start discharging from this charged value, and the capacitor voltage start decreasing, and it would go towards minus VCC. So this voltage first becomes 0, and it would start increasing towards the negative level of minus VCC. So this would go to minus VCC. Now here we have already some negative potential defined by this relationship, and trigger point is set at this point. This trigger point is some negative value, and this voltage of the other terminal, which is defined as V2, is now decreasing and becomes negative. And as long as this voltage becomes more negative than this voltage, then what happens is this potential would become higher than this potential, then output becomes plus VCC. So at the instant where the voltage at the negative terminal becomes more negative than the voltage at the non-inverting terminal, which is as minus V1, then output would flips to plus VCC. Now this output becomes plus VCC. So when this output becomes plus VCC, then this also becomes plus V1, or becomes UTP, and with plus here the capacitor would start charging towards VCC with initial voltage which was defined as minus V1. So here the capacitor was charged to some negative value, and from this negative value capacitor would start charging up, and at the instant when this capacitor voltage reaches to a value which become equal to V1 and further increases from this level, then this voltage would be higher than this voltage, output would flip to negative saturation level, and this process will keep on continuing, and you will get the output at this point with the square wave, free running square wave with certain time period and frequency that we will compute in the coming slides. So this circuit is also called the relaxation or oscillator. the output would be relaxing at a certain with a certain pattern and with certain frequency. So first of all, towards the analysis of the timing calculations, first we see how the time period of the output can be calculated. So in order to determine the time period and the corresponding frequency of the output wave, we can proceed as follows. So first we find out the high and low times of the square wave as indicated in the figure. So this is the duration in which the output stays at high level, which is defined as T high, and this is the duration in which output stays at minus VCC or at low level, which is defined as T low. And we can see from the figure that the T high is the time expanded during which the capacitor is charged from LTP to UTP. So T high is the time duration during which the capacitor is charged from LTP to UTP. So how much time the capacitor would take to charge from this value to this value, for that time interval the output would stay at high level, and once it reaches at this trigger point, then output would switch to low level. And how much duration it would stay at the low level? As long as the capacitor voltage would start changing from UTP to LTP, for that duration the output would stay at low. So T low is the time expanded during which the capacitor is charged from UTP to LTP. So these durations T high and T low would solely depend upon the time it taken for the capacitor to charge from one trigger point to the other trigger point, from UTP to LTP or from LTP to UTP or from UTP to LTP. Now let me first compute the time TH. So for that we have to recall from the capacitor charging equation, as we know from our earlier circuit analysis course that a capacitor is charged and the when capacitor is applied some voltage, as you can see in this circuit diagram, that for this capacitor, if this capacitor is charged through a resistor and a voltage is applied, when this switch is at position 1, the capacitor would start charging up towards this value E, and the equation that governs the charging of this capacitor is defined as VE into 1 minus e to the power minus t by R into C, where R and C is the time constant. This is R1, this is R1 into C, and T is the variable that changes from 0 to infinity. So as time progresses, the capacitor voltage would behave and it would follow this equation. But with some initial charge on the capacitor, if there is some initial charge on the capacitor, for example, if there is some initial voltage, let's say 2 volts, then this equation is modified and is written in this form as Vc is equal to VE minus VI, where VI is the initial voltage of, for example, 2 volts into 1 minus e power minus t by R1 into C minus VI. So this is the equation which is used whenever there is an initial charge in a capacitor, and then capacitor is charged further with the application of any applied voltage. So capacitor would charge from the initial value, and it would be charged up to this applied voltage. So for this case, for example, if I initially capacitor voltage is at 2 volts and this switch is closed and is at position 1, and it remains at position 1 for indefinite time, then after time infinity the capacitor would charge to this applied voltage of E volts. For example, if E is 10 volts, then after 5 time constant the capacitor voltage would be equal to 10 volts. So this is the equation that we will be using for the analysis of our oscillator circuit. This is further modified after some manipulation and end up with this relationship. So this is the relationship that we are going to use. So this is the profile of the capacitor charge, capacitor voltage for a condition in which there is some initial voltage at a capacitor, and the capacitor would start charging from its initial value and charge up to the applied voltage. So this is the same equation. Now to find TH, which is the time during which the capacitor is charging from the initial value of VLTP to the final value of VCC. While charging toward VCC, the time at which the capacitor voltage reached to VUTP would be the required duration TH. So in this case, from this equation, what is VI? V is the initial voltage for the time interval TH, that is the time from which we are starting to calculate the duration of this time interval, that the initial voltage of the capacitor was T high, initial voltage on the capacitor was VLTP, and the final voltage where the capacitor is would to keep on charging or would ultimately go is VCC, and the voltage at which the the time at which the capacitor would reach at UTP, or the voltage where the capacitor would reach at UTP is and the time after which the capacitor would reach at the level of VUTP is TH, and the voltage at the after this time would be equal to VUTP. So by putting these three quantities, that is VI, VE and VC of t, VI, VE and VC of t, and the fourth one is T is equal to TH, this time starting from 0 to TH. The equation 1 would become as Vc of t at t is equal to th would be VUTP. That would be equal to Vi is VLTP minus VCC. V is VCC. This is the final value. Into e to the power minus t is t high divided by R1 into C. R1 and C is the time constant, plus VE, which is V is VCC. So by applying this equation for our scenario in the oscillator circuit, we end up with this relationship, and from this relationship we can further move to find out the value of TH. So when we simplify this relationship, before that we plug the values of UTP and VLTP. UTP is defined as this, VLTP is defined as this. So if we plug these two in this equation, then we will get this equation, and from which we can further simplify, as with this VCC is cancelled with this, we can take common from this equation, and then it would be cancelled. Then after rearranging these terms and to solve this equation for TH, we can further see that this term is cancelled with this, and then moving it to the other side and taking the natural log on both sides, this log and E cancels, and we end up with T high is equal to minus R1 into C log of this expression, and then this minus can be omitted by reversing this ratio, and finally TH would become equal to R1 into C log of R2 plus 2R3 divided by R2. So this is how you compute the duration of the output waveform during which the output stays at the high level. Similarly, we can follow the same procedure to determine the expression for T low. I would encourage you to find out the similar expression for T low by using the capacitor equation, and then setting the initial and final conditions, and plugging the values and simplifying, then end up with this expression. So you will get the expression for T low similar to T high, which is T low is equal to R1 into C log of R2 plus 2R3 divided by R2. We can see from the expression for T high and T low that T high is equal to T low, as the time required to charge the capacitor from UTP to LTP is equal to the time required for the capacitor to charge from LTP to UTP. So in both cases the capacitor is charging through this resistance R1. So in either case the time required to jump from one level to the other level would remain the same. So these two time intervals would be equal, and the time period we know is T high plus T low, which would be equal to 2 times this time, this expression. And from this, if we know time period, we can find out frequency, as the frequency is equal to 1 over time period, and plugging the value of time period from this relationship, we have frequency equal to this 1 over this expression. So that's it for today from this square wave oscillator, and next time we will see more oscillator circuits, in which we will see a triangular wave oscillator, sawtooth wave oscillator, and sinusoidal oscillators.